You know how much work goes into building a great AI model? You train it, you test it, you deploy it, and then what? Well, that's where a really sneaky problem can creep in, one that can make all your hard work for nothing. We're talking about AI model drift.
So let me ask you something. What if your model, which is out there in the wild making predictions, is slowly becoming less and less accurate, but all the dashboards look green? This isn't some far-off possibility. It's a huge risk for any AI system that's actually being used. It's a silent failure just waiting to happen.
And the culprit, the root cause of this problem, has a name: distribution drift. It's really simple when you think about it. The world isn't static, right? Your users change, the market changes, and the data you're feeding your model in production starts to look totally different from that nice, clean data you trained it on. And when that happens, your model is basically flying blind.
So here's what we're going to cover. We'll start by digging a little deeper into this silent failure mode. Then we'll get practical with a drift detection toolkit. We'll walk through how to detect feature drift and how to monitor your model's predictive uncertainty. We'll even look at a cool twist in reinforcement learning. And finally, we'll wrap up with why all of this is so critical for you.
Okay, theory is one thing, but what you really want is a practical solution, right? Something you can actually use. That's why today, we're walking through a hands-on GitHub repository that's built to give you the exact tools you need to spot drift. Think of it as our playbook. The repo is super straightforward. It's built around three main notebooks. First, there's drift simulation, which is our main example for supervised learning. Then there's a handy script just for plotting the drift, and later on, we'll get into drift RL to see how this all applies to reinforcement learning.
All right, let's dive in and get our hands dirty. First up, we're going to tackle how to detect drift in the actual input data your model is seeing. This is all about spotting the exact moment your model starts seeing data it wasn't trained for. Now, to keep things really clear and simple, the main notebook, driftsimulation.ipynb, uses the classic iris dataset and a random forest classifier. It's a setup most of us know, which means we can focus on the drift detection itself without getting bogged down in a complex problem.
And the actual process here, it's honestly so simple but incredibly powerful. First, you need a baseline. You take your original training data and say, this is what normal looks like. Then, for new data, you start measuring the difference. Step 3 is the secret sauce. You calculate something called KL divergence for every single feature. And finally, you visualize it, so you can see with your own eyes which features are going off the rails.
So what is this KL divergence thing? Well, you don't have to be a statistician to get it. Just think of it as a score that measures how surprising the new data is compared to the old data. If the score is low, everything's cool. But a high KL divergence score, that's your big red flag. It's an alarm bell screaming that one of your features has drifted way off course.
Okay, so checking the input data is huge, but it's only half the story. There's another super powerful signal you can track, and that's by looking at your model's output. Basically asking the model, hey, how sure are you about that prediction? This is what we call monitoring predictive uncertainty.
And the tool for that is called predictive entropy. The absolute easiest way to think about this is as your model's confusion score. See, when a model gets data it's never seen before, data that's drifted, it gets less confident. Instead of one clear answer, its predictions get spread out. High entropy is the number that tells you the model is just not very sure of itself anymore.
And this is where it gets really practical. You can literally set a threshold. If the entropy for a prediction is too high, you can just automatically flag it. This means you can catch bad predictions before they affect a customer or a business decision. It's a proactive safety net. Now, this whole idea of drift, it's not just for supervised learning models. Things get really interesting when we apply the same thinking to reinforcement learning systems, because drift looks a little different there.
And this comparison lays it out perfectly. In supervised learning, we're worried about our input features changing. But with reinforcement learning, your agent is interacting with a whole environment. So drift can happen when the environment itself changes. Maybe the rules of the game get tweaked or the physics are slightly different. It's a much more dynamic kind of drift.
The repository has a great example of this in that drift RL notebook. It takes the classic CartPole game, where an agent has to balance a pole. But then it simulates drift by slightly messing with the observations the agent gets. That tiny change is enough to completely throw the agent off its game, and it shows you just how fragile these systems can be to environmental shifts.
So, we've walked through the concepts, the metrics, and the code. Now let's just bring it all home. Why is this stuff not just a cool academic exercise, but something you absolutely need to be thinking about for any AI you put into production?
Well, the takeaways are pretty clear. This gives you the power to know the exact moment your model is operating on shaky ground. It lets you prevent costly mistakes from bad predictions. It also takes the guesswork out of retraining. No more retraining on a schedule. You retrain when the data tells you to. At the end of the day, all of this adds up to building AI systems that are just more robust, more reliable, and frankly, more trustworthy.
I'll just leave you with this one thought. Your data is not static. It is changing, right now, as we speak. So the question you really need to be asking yourself isn't if your model will experience drift, but when, and is your system actually ready for it?